There are many kinds of data in this world. So some of them are simple, like the day of the week, maybe a street name, or the number of steps you walked today. And some are complex because it's volatile, it's frequently updated. It's also widely distributed to a diverse set of audiences and has to be compliant and follow business rules. There are many kinds of complex data in this world, but the ones that we're interested in is what we call core business data. Core business data often are complex, but it's extremely valuable to the business because it has to be used to improve its competitive advantage in the market. Some examples of core business data include things like a customer profile, their preferences, a patient's medical electronic health records, banking account and transactions, and things like sales transaction and agreements. The problem with core business data is that systems that processes them are often complex as well. They're not easy to understand and it's hard to change. Complex systems are hard to understand because it often involves many numbers of different systems or stakeholders. And they're often interconnected and interdependent as well too. Complex systems are hard to change because any change in this kind of system can cause a ripple effect that has huge impact across the entire ecosystem. In a world that is becoming more and more complex, this drives up the cost of managing core data, and this in turn hurts the business's capability to gather deeper insight and to adapt to an ever-changing market. And since databases are the primary storage of core business data, it plays a critical role in this problem. So let's talk about how a traditional database has historically been working with complex and core business data. So traditional databases such as relational has been the de facto database in the industry since it went mainstream in the 1990s. It was designed to provide transactional consistency across core business data, which works well for applications that typically have strict business rules. So an example of this is say like a wire transfer between two accounts. You won't want the bank to mess that up. So transactional consistency ensures that a series of actions in a system are carried out completely and correctly or just not at all. And this prevents the system from ending up in an unpredictable or erroneous state. And as a result, users can trust the system to maintain its integrity even after a lot of complicated actions. However, shortly after the internet went supernova in the early 2000s, developers discovered that it was hard to distribute data to more and more external systems. Well, this is because applications that use traditional database were primarily designed for transactional consistency. And transactional consistency doesn't really scale well, especially at that internet scale. There are a few reasons why that's the case, but we can boil it down to its problem when it comes to scaling it vertically and horizontally. Transactional consistency is hard to scale up because it requires you to upgrade the resources for one single server. So the CPU, memory, storage, network, and so on and so on. And since it gets progressively harder and harder to increase the resources for a single server, this means that there is an upper limit to how much it can actually vertically grow. And this can only be improved up to a certain point. Secondly, with only a single server managing your data, it also means that there is one single point of failure. And since database is a critical piece of infrastructure, when it fails, the entire system goes down with it. And lastly, it is also prone to concurrency issues when there is an increased amount of transactions. And this can cause race conditions, deadlocks, and other things that massively just slows down the database. And on the other hand, transactional consistency is also hard to scale out because it typically requires distributed transaction across multiple servers. And this slows due to latency and extra round trips that's required between the servers to make sure the change can be executed consistently across all of them. And finally, transactional consistency is also error prone because failure in any server will fail the transaction on all servers. And so as the number of participants increases, the risk of failure increases in a non-linear way as well. So as we see, transactional consistency is not really easy to scale up and out. But however, back in the days, developers continued to use it because there was just no better choice at that time. And this, along with the complexity of core business data, started to result in databases that were just huge, monolithic, tightly coupled to many parts of the system. And this brings us to the rise of eventual consistency in the 2010s. So with the popularity of cloud and big data in the 2010s, demand for data distribution continued to skyrocket. And because the scalability and the coupling issues that come with transactional consistency, many developers began to look for something else. And what they found were integration patterns that utilizes eventual consistency instead. Eventual consistency ensures that a system will become consistent over time given that no new updates are made. While users may see outdated data temporarily, the system guarantees that all systems will eventually converge into the same value. This may sound a little scary at first, but it actually allows the system to provide much higher scalability and looser coupling, even at the cost of immediate consistency. So we can compare transactional and eventual consistency in a few different ways. When it comes to transactional consistency, all the systems are either synchronized at once or not at all. Eventual consistency, on the other hand, promises that systems will be synchronized eventually. When it comes to coupling and scalability, transactionally consistent systems tend to be more tightly coupled. And this is because it requires all the system to immediately reflect changes. It makes them highly interdependent. And this interdependency means tighter coupling, since each system relies heavily on each other to function properly. This often leads to lower scalability as well too. And on the flip side, eventual consistency generally leads to systems that are more loosely coupled. And this is because systems are allowed to update at their own pace. And this approach fosters more independence between the systems, resulting in looser coupling as they don't need to coordinate instantly. And this makes eventual consistency much more easier to scale. To understand the difference between transactional and eventual consistency, we can also compare similar communication patterns. So for example, face-to-face communication can be compared to transactional consistency where instant responses is required by multiple parties. So text messaging, on the other hand, is like eventual consistency because it doesn't need immediate response from everybody and it's more hassle-free. Another way to describe transactional consistency is say that it's synchronous or two-way communication pattern where eventual consistency is more like a asynchronous or one-way messaging pattern. And finally, when it comes to software development, transactional consistency often uses request-response type of communication protocol, where eventual consistency uses publish-subscribe more often. Now that we understand the difference between transactional and eventual consistency, let's take a look at how it evolved over time. So, eventual consistency is not a new concept. Scheduled jobs, ETLs have been popular since the 1990s. However, there was a huge uptake of new event-driven solutions that supported eventual consistency during the 2000s and the 2010s. These tools include things like message queues, brokers, and practices like event-driven architecture. And these solutions help made it simpler for developers to implement event-driven applications. So while these solutions have been immensely helpful in advancement of eventual consistent operations, it still takes a lot of work and skills to develop fully decoupled and scalable systems. The common problem with these event-driven solutions is that they're still built on top of data that comes from traditional databases. Problems such as message duplications, message being out of order happens all the time in distributed systems and in the world of eventual consistency. And this is not trivial to handle, even with these newly developed event-driven solutions. A large part of this is caused by the fact that data is still captured in traditional databases, which doesn't have the proper features to support eventual consistency. Event sourcing and state transition databases, on the other hand, is designed with eventual consistency in mind, and it's the better alternative to decouple complex systems.